Okay, guys, this is Unit 3, dealing with the atomic structure and the atomic theory, along with some of the last parts we'll be dealing with the quantum theory of the atom. Please watch this video in its entirety because we'll be doing some demonstrations based off this in the next couple of days. First person we want to talk about in a historical aspect is Democritus. Democritus was not a scientist, he was a Greek philosopher, and he was credited basically being the first person to have the idea that all matter has to be divisible, and you can break it down into smaller and smaller pieces, and at some point you have to get to an end of that division, and the end of that division is what we now call the atom. We're talking about 400 BC right here, and really not a scientist, not a person who did an experimentation, just kind of developed that idea that there has to be building blocks within nature. Move forward to the early 1800s, and now we get the first scientist who really talked about the atomic theory. John Dalton is accredited for being the first scientific atomic theory, and his atomic theory had 5 parts to it. The first 2 parts you see on the screen. Number 1 being all matter is made of indivisible and indestructible atoms. If you think about this statement, indivisible and indestructible atoms, in the early 1800s, as far as they knew, this was a true statement, and this was something that held up to all their research. We now know that this is not 100% true. We have been able to show that we can split atoms through fission, and we also know that the atoms are divisible. We can break them down into smaller particles such as protons, neutrons, and electrons. So his first atomic theory isn't considered to be 100% accurate anymore. We still use it as a baseline for what the atom is made of, but we also basically have modified it over that time to now include the idea of fission, protons, neutrons, electrons, and even more specifically now into the world of quarks and things that build the protons and neutrons. His second part of his theory tells us that all atoms of a given element are identical in their chemical and physical properties. That sounds like it's a pretty good statement. There's one small piece here that's a little bit mistaken, though. He says all atoms of an element are identical. We now know that elements have multiple versions of them called isotopes. So, again, a slight modification on his original theory to basically talk about what an isotope is. You guys have heard of carbon-12 before and carbon-14 before, used in carbon dating. Carbon-12 is our stable form of carbon. Carbon-14 is the unstable or radioactive form. So over time, carbon-14 decays and disappears, so we can actually date living or past living objects by how much carbon-14 is left over in those cells. His statement doesn't really talk about isotopes at all. So you could easily fix this and say that all isotopes of a given element are identical. All atoms of a particular isotope of an element. So all atoms of an isotope of an element are identical, because carbon-12 is identical to other carbon-12 as far as we know, but carbon-14 and carbon-12 are not identical chemically because they have different numbers of neutrons in them. So first 2 parts, not 100% accurate in terms of what we believe now, but still are very good baseline information for his theory. Parts 3 and 4 still hold true to everything we believe today. So atoms of different elements combined in simple whole number ratios to form compounds. Basically this part he's saying that to make compounds you can't use a half an atom. You have to use individual atoms or whole number ratios with that. And then chemical reactions would consist of separation, combination, or rearrangement of atoms. You gotta remember, in the early 1800s, the concept of things like lead turning into gold and alchemy was still relatively prevalent. So to come out and say that chemistry only can separate atoms, combine them, or rearrange them, what he's basically saying is you can't turn one thing into something else magically. That all it is basically a rearrangement of atoms. So it's kind of a powerful statement for that time period, even though today we kind of see this as common sense. Back then it really wasn't. So Dalton's atomic theory has 4 major parts to it, and then within that, the first 2 parts weren't 100% accurate from his timeline. From Dalton's atomic theory, he was actually able to develop the first model. So as we go through the notes, we'll talk about different theories and different historical backgrounds, and then the models that came from that. So his model was as basic as it possibly can be. He believed an atom was the smallest particle. He believed it was indivisible and was not separatable. So as a result, his model shows that the atom would be kind of like a sphere, where it would just be a solid sphere or a ball of mass that was indestructible. You could not break it apart and had no complexity to it. We now know that his model isn't right, that there's more complexity there. However, it was a good starting point from a historical aspect. Again, we're talking early 1800s. Moving on from Dalton, we move into this idea of what was done next. So late 1800s, early 1900s, we started doing experimentation, and the technology was catching up to some of the different ideas about what's possible inside the atom. And one of those discoveries, actually the first one, was the discovery of the electron. This was done by using a device called a cathode ray tube by J.J. Thomson. Basically what J.J. Thomson did, he was able to beam a ray of particles from a power source through a vacuum tube, and that beam would hit the backside of a screen. And that screen was coated with phosphor. And what phosphor does is it glows when basically electrons hit it. He was able to show that this beam of electrons coming across here existed by using this evacuated tube, or basically a vacuum chamber. And we call that a cathode ray tube because you have a cathode at one side, a little opening where the anode is to allow the electrons to flow through that opening and then pass through the beam. The way he was able to do that is not only was he able to determine the beam existed, but he was also able to use magnetic plates called condenser plates with a positive and negative charge to them, or a magnetic charge to them. And that charge would then bend the beam in certain directions. And using very, very precise measurements and repeated measurements, he was able to determine the power of his charge versus the bend of the beam, that he actually was able to pick up a mass that was less than that of an atom. So the particle that he was creating this beam was not atoms, it was actually something smaller. And it had a negative charge, so that was the electron. Next slide is a video for you guys that kind of explains that in more detail.
Thomson didn't discover the electron.
Well, it's of course said that way, but he didn't discover in the sense that he said, Eureka, I've got this thing, here it is. He did an experiment that allowed him to measure the ratio of the charge, the electric charge, to the mass. And then later he was able to get a rough measurement of the charge and therefore show that the mass was very, very small. It was about 1/2000th of the mass of the lightest known atom, hydrogen atom. So it showed that he could extract in the experiment a very small piece of an atom. Well, that was a tremendous shock. People didn't
Pun
imagine.
intended.
Yes, yes. Electrical piece of an atom. It was a very small part of the atom.
At the time of his discovery, Thomson was a professor at England's University of Cambridge. He was using a device called a Crookes tube in his experiments.
I happen to have here a little apparatus that's akin to the one that J.J. Thomson used in 1897. It's called a cathode ray tube, just an evacuated little glass cylinder with some electrodes. And we can hook this up and show the key points of his experiment.
A replica of the first CRT.
Yeah. It's the first cathode ray tube. It's ancestor of the television tube, as a matter of fact. You do the last one, and we should get a stream of cathode rays or electrons going there, and it'll show up. A few of them bang into this phosphor-coated piece of cardboard there. Here, I'll give you a magnetic field you can use to deflect the electrons.
When Thomson exposed the stream of cathode rays to a magnet, the stream would bend. Since magnets can only affect matter, this meant the stream of rays was composed of some kind of electrically charged substance called radiant matter. After many hours of observing and measuring, Thomson realized he'd found the first subatomic particles. The ray was a stream of electrons. It was a revolutionary discovery.
Okay, so from his experiments with the cathode ray tube, he actually was able to update and modify the current understanding of the atom, and he came up with his own model, which he dubbed the Plum pudding model. Now, I'm of firm belief that many of us in this world do not know what plum pudding is anymore. I personally don't really know what it is, to be honest with you. I've been told it's some sort of bread with like raisins and craisins and other nuts and stuff in it. But nevertheless, the idea behind his model, which we still do call the plum pudding model because that's what he called it, is that there's a ball, a positive kind of dough-like material that makes up the atom. And then embedded inside that positive dough are all these particles, these negatively charged particles, which we call the electrons. Myself, I visualize it more like a chocolate chip cookie. Or if you see the delicious chocolate chip cookie, the cookie part is like your positive dough, and the chips are kind of like your negative electrons. In his model, there is no nucleus, there are no protons and no neutrons yet, because none of these parts of the atom were to be discovered yet. So really all he added in was that this positively charged mass had negatively charged particles somehow embedded in it, and we call that the plum pudding model. The next key piece that was discovered by Ernest Rutherford. Again, we're working in the late 1800s, early 1900s. This was done after the electron. And believe it or not, the next thing to be discovered was the nucleus of the atom. To do that, Rutherford had to run an experiment using gold foil. So here's a little video on his experiment.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most
alpha particles, for you guys, just so you guys know, are basically taking a helium atom and getting rid of all the electrons, and all that's left over is a nucleus of a helium atom. That's basically what an alpha particle is. So basically it's a positively charged helium atom flying around.
The alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, so if we take a look at this idea of his gold foil experiment, this is one of the more famous experiments in the atomic theory world. Basically what he did is he beamed these alpha particles through really thin gold foil. Gold is very malleable, so you can make it extremely thin so you don't have much thickness there and very few atoms thick. By varying the width, or how wide he allowed the beam of alpha particles to go, and calculating the percentage of ones that were deflected and at what angle they reflected around the screen, he was actually mathematically able to get a rough estimate of how big the massive core was compared to the outer part of the atom, which was essentially empty space, which we now know as the electron cloud. Because the alpha particles were positively charged and the nucleus was positively charged, when they got close to each other, they would deflect away, like two positive sides of a magnet, or two north poles or two south poles. So this deflection was created by that charge repulsion inside there. The big conclusion from this was that the atom is mostly empty space, except for a central positive mass in concentration, which we now call the nucleus. At that point, he was just calling it, the center of it was just very massive compared to the outer space that was not, and we now call that the nucleus of the atom. From this discovery, from this experiment, we had yet another model of the atom developed. So every discovery, every experiment build our knowledge of what the atom looks like. So Rutherford is able to tell us atom has a very small, massive center core. It's positively charged. Most of the atom is empty space. And in that empty space are the electrons. A couple of things about this model, the nuclear model. He has yet to talk about how the electrons are moving. So they know they're out there. They don't really know how they're moving yet, not orbiting yet. So really, in the nuclear model, all we've really done is taken the idea of evenly spread out mass, condensed all the mass to the center core, and have put the electrons in this empty void around this massive core for a nuclear atom. And we haven't talked about how those electrons are moving yet. Once we've had the nucleus discovered, the next key piece of the puzzle was discovering the proton. The proton really is accredited to several different scientists. The two most commonly ones you'll notice are Eugene Goldstein. Goldstein ran a very similar experiment that J.J. Thomson did in terms of using a cathode ray tube, but he reversed the polarity on the tube, and as a result he was actually able to detect positively charged flow. And with positively charged flow, that gave us the idea of there is positively charged particles out there. Now in reality, his experiment was just showing positively charged ions, so he really wasn't producing pure protons, but it was a very key step in this process. And then in 1918, again, Rutherford, with his alpha particles, he liked to beam those at all kinds of things. He was actually pushing those through concentrated or compressed nitrogen gas. And those alpha particles colliding with the nitrogen molecules actually caused a reaction which created or split off hydrogen ions. Well, as hydrogen ions got expelled, they basically were protons. If you imagine a hydrogen atom, this picture over here, a hydrogen atom is one proton, one electron. That's all that's there. There's really nothing else that makes up hydrogen. So if you get rid of the electron and you just have the ion or just the proton left over, by removing the one electron for hydrogen, you basically get protons. That concept is still used today in our most sophisticated particle accelerators. If they want to get a bunch of protons to beam around, they just strip the electrons off of hydrogen, and they now have a bunch of protons to work with. So Goldstein kind of started the process, and then Rutherford basically was able to finish it in terms of the discovery of the proton. The last key particle that was discovered was a neutron by a guy named James Chadwick, 1932. What he did is he used beryllium radiation, or basically radioactive beryllium, and was beaming it into a paraffin wax, which is a kind of a dense wax. And what he found was that the particles were actually embedding further into the wax than they should have if you just calculate the mass of the proton and electrons there. And actually, he was determining that they were almost embedding twice as far as they should. So the mass must be double that they expected it to be. Well, from that experiment and from those calculations he did with the experiment, he was able to deduce that there was another set of particles that we now call the neutron, that was also part of that nucleus or the core of the atom. So the question kind of arises, why is the neutron the last one to be found? Well, if you think about it, the first two particles found were found because they had a charge to them. So electrons are negatively charged, protons are positively charged, and we were able to use that charge to basically pull them out and to identify them. Neutrons are neutral, so with no electronic charge, they're much harder to determine and figure out. Little side note, we now know that inside the neutrons and inside protons, so neutrons and protons, we have even smaller particles called quarks. These particles called quarks make up the actual protons and neutrons. It's not the focus of this unit, but it is interesting that we do have even subatomic particles that we now are researching and discovering and working with, that actually starts to map out how the neutron is made and how the proton is made. Not the electron. The electron actually is found to be more on the size and scale of the quarks in terms of what they are. All right, we're going to stop here today. Thank you guys.